We will now explain another kind of designs that are extremely important, that is factorial designs. So factorial designs are those designs in which we have multiple factors that may affect the results. And let's start with an example. So let's say that we are measuring the effect of a treatment on a number of animals as a function of age and sex. So age and sex are called factors, and the different values are called levels. So male, female, or young or old would be levels within the age and sex factors. For each combination, we have n equals 6 animals, and our model, so we have 4 groups. So we have young males, young females, old females, well, all the possible combinations, and then these are the means of each one of the groups. So we have an overall mean that is 5, and then each one of the groups is contributing with a different amount. So this would be similar to the completely randomized designs that we had before. And the problem with this is that we see that not all the groups are the same. Let's say that these differences are significant. So not all the groups are the same, but we don't know why. So we see that young males are different, old females are different, but we don't know exactly what is making the difference. It is the age or it is the sex. So what we can do is to try to attribute all these differences to the different factors. So instead of having this design as we had before, actually the design is a way of analyzing the data, and it has its implications at the level of before doing the experiment, because as we saw before, we have to make homogeneous groups, and then the homogeneous groups have to be given to the control treatment. So we make homogeneous groups, and then in these homogeneous groups we see that this average was these are young males, the average is 7, and the same old males are here, the average is 5. And so we have distributed now the averages that we see for the groups 7, 5, 5, 3. We have distributed them in a table, and in this table we will try to identify what is the contribution of age, of sex, and the overall mean. So the overall mean is 5, we put it here, and then the average, what is the average of males? So what is the contribution of males? We saw it before, so we have to compute the mean of males, that is 6, and this mean of males minus the overall mean is the contribution of males. So males contribute with 1. Females, the average is 4, so females contribute with -1, and we see again this constraint that males plus females have to add up to 0. And the same for young. So of young animals, the average is 6. 6 minus the overall mean is 1. And old animals, the average is 4. And 4 minus 5 is -1. And again, we have the addition of 0. Okay, so now when we have to explain this 7, we have a much better tool, because we can say, okay, so this 7 is the overall mean plus something that depends on the age, that is +1 because you are young, and plus something that depends on the sex, that is +1 because you are male. So 5 plus 1 plus 1 is 7. And then the female that you observe 5, now it is 5 plus 1 because you are young, -1 because you are female, and the same for all the other cells. So now you see that young males and old females are different, and you know the reason why. So the reason is that male female, they have a difference of 2 between them. So from this +1 to this -1, there is a total distance of 2. The same happens for young and old, and then these two zeros that we saw in this group is because the extra +1 of young cancel with the extra -1 of females, and the same for old and males. So now you see that not all the groups are the same, and you also know why. You know which is the contribution of each one of the factors. And we can, so this is the same table that we had before, and now we can try to represent this graphically. So for instance, you would have, you can do it in two axes. So this is the response, and this is one of the factors, that is male female. This is the other factor, that is young old. So in the male female you would have two lines, so one for young animals and another one for old animals, and you see that they are parallel and their difference is 2, and this 2 is the difference that you have between young and old animals. So these young and old animals, we were saying from here to there is a distance 2, so this is the same distance 2 that we have in here. And the same happens with male and female. So if this axis now is young and old, then the male and females, they are separated by 2. And the fact that these two lines are parallel and these two lines are parallel is an indication that you only have main effects. Main effects are these contributions from each one of the factors independently. Okay, so let's see another example. So let's say that now our observations are 6, 4, 6, 4. Now we do the same kind of calculation that we had before. So the overall mean is 5, and then the contribution, this mean is 6, and then 6 minus 5, it is the +1 that you get for being young, and this average is 4. 4 minus 5 is -1, that is this -1 that you get in the for being old, and then the average of males and the averages of female are 5 both, so you get an extra 0 if for the sex. So we see that age makes a difference, but sex does not. So you have now if you make the same kind of plots that we were doing before, so now you see that these two lines are again parallel, and but male and female they are coincident, so it is the same line, and the reason is that there is no difference between males and females. So you have main effects if those line representations are parallel or coincident. Okay, so let's say that now our measurements are 6, 4, 4, 6. So we do the same kind of decomposition that we did before. So the overall mean is 5, but the mean of males is also 5. The mean of females is 5, so the contribution of male and females are 0. And the same for the ages. So the ages, the mean is 5, and you get an extra 0. And for old animals, the mean is also 5, so you get 0. But yeah, here there is a mistake. This should be 5. Okay, but then I cannot explain my data because I cannot see that. So when I try to explain a cell, it is the overall mean plus the contribution of your age plus the contribution of your sex. But the contribution of age and sex is 0 in both cases. So I would have 5, and 5 doesn't add up to 6. So there is some mismatch, and the same happens in all other cells. So there is a mismatch that I'm not able to explain. When I make these plots, what I see is that the lines cross. So a crossing lines or different slopes for each one of these lines calls for something that are called interactions that we have not introduced so far, and we do it now. So the interactions are between factors. So interactions are when a factor, the influence of a factor depends on the level of the other factor. So, for instance, for young animals, male young animals, so you have male and female animals. So for male, young is contributing positively, while for female, young is contributing negatively. And the same for old. So male old contributes negative, while old female contributes positively. So now the interaction is the difference between the mean of the group and the mean, so whatever you have, the mean of the group and what you have explained with the main effects only. So for instance, this 6 before we were able to explain 5 plus 0 plus 0. So there is a difference between 5 plus 0 plus 0 and 6, that is an extra 1. So the extra 1 is the contribution of this group, so of the interaction of this group. So young males, they contribute with +1, and the same here. So females, I was able to explain up to 5, but then the difference between 5 and 4, that is what I observed, this -1, is the contribution of the interaction between young females. So you do the same for all other cells, and now you have the contribution of the composition of your observations as explanatory variables. So you have the contribution of age, the contribution of sex, the contribution of the interaction between the two, and then something that depends on a specific animal. And this is well, okay, so we have already introduced interactions. Interactions happen between factors, not between levels. And also there is an interesting property, that is that you may remember that the age, all they have to add up to 0, and the same for sex. So the same happens for the interactions, and they are constrained, even more constrained than the main effects, because they have to add up to 0 if you sum by age or if you sum by sex. So if we sum by age, you see +1 -1 is 0, -1 +1 is 0, and if we sum by sex, +1 -1 is 0, -1 +1 is 0. So that means that it is so much constrained that given one of them, given one of these numbers, you automatically know the other 3. So if you are given that this is +1, this has to be -1, because the addition of the 2 has to be 0. And if this is +1, this has to be -1, because the addition of the 2 are 0. And if this is -1, then this has to be +1, because the addition of these 2 has to be 0. So interactions are extremely cheap, and they may explain a big part of the variability of the data, and they may be needed to explain the means that you observe in each one of the cells. So now, in general, the composition, our linear model will be this one. So whatever you observe is an overall mean plus something that depends on the first factor, plus something that depends on the second factor, plus something that depends on the interaction between the two, plus something that depends on the specific animal. And then the constraints are the sum of all the main effects are 0. So for P, for Q, these two constraints. And then if you sum over P, the interactions, they have to be 0. If you sum over Q, they have to be 0. And then how to estimate these things. So these equations are only valid for balanced designs. But so the mean, the overall mean is the mean of all samples. The main effects we have already seen. So this would be the mean of males minus the overall mean, the mean of females minus the overall mean, and then the same for the age. And then the interactions is the mean of the group minus whatever I have explained. So minus whatever I have explained can be expressed in this way, and then the estimate of the contribution of each animal is the observation of that animal minus the mean of its group. And, and we can make the same sum of the squares decomposition. So we will have the overall the total sum of squares with n minus 1 degrees of freedom, the part that is explained by the first factor, the part that is explained by the second factor, the interaction of the two, and the number of degrees of freedom is p minus 1, q minus 1, where p and q are the number of levels in the first and the second factor, and the number of degrees of freedom for the residuals is whatever is left. That particularly is this thing. So we would come out with the same ANOVA table as we did before, and we would compute the mean squares for each one of the contributions. And when you want to know if something is significant, you have to compare the mean of squares of that factor to the mean of squares of the residuals. That is the part that you have not explained. So here there is an example. So let's say that you are testing water uptake by amphibia, and you want to know what is the effect of a mammalian water balance hormone on this amphibia. So mammalians and amphibia, they are relatively apart in the evolution. So we want to see if this mammalian hormone of water balance has an effect on amphibia. Okay, so we think that there could be, so it depends on the type of amphibia. So we take a couple of species, let's say frogs and toads. So we have the first factor S. Then our experiment will weight the animals before doing the experiment. Then we apply the treatment, and then that is either I give the hormone yes or no, and then I will put them in water for half an hour, and I will take them out and weight them again, and the difference between the two measurements will be my observation. And because the amount of water that the animal takes may depend on whether the animal was before in water or not. So let's say that my experiment takes half an hour, but before this half an hour, what has happened? The animal was dry or was wet. So if it was wet, maybe it is already saturated and it doesn't take any water. So it doesn't incorporate any water. So I will define a new factor that will be this moisture factor. So I will have the animals half an hour, also let's say 1 hour before doing my experiment, 1 hour in water or not. So I will define these dry or wet animals. Okay, so for each one of these combinations I have 3 factors. I have 2 levels in each one of the factors, so the total number of combinations is 2 to the 3, so 2 levels to the power 3, because I have 3 factors. So I have 8 possible combinations, and for each one of these combinations I will have 2 animals, and for each animal, so I have what is your species, that I will call I, what is your moisture condition before doing the experiment, that I will call J. We have the hormone or not hormone, that we will call K, and for each one of these I, J, K combination we will have a couple of animals. So L takes the values 1 or 2 depending on whether you are the first or the second animal in that combination. So for a given animal, what we see is an overall mean plus something that depends on the species plus something that depends on your wet or dry condition before, plus something that depends on the hormone, plus the double interactions, and there is a mistake here in the formula. I should have included the triple interactions. And now you make your analysis, you compute all these sum of squares that we have indicated here, and these are the numbers that you get. Okay, so in total you have a variability, a sum of squares of almost 1800, and this is the decomposition in the different contributors. You count the number of degrees of freedom. So we had 16 animals in total, so that means that we have 15 degrees of freedom, and then each one of these factors has two levels, so we need 1 degree of freedom for each one of the factors. So this is 1, this is 1, this is 1, and the interactions, you may remember, it is p minus 1, q minus 1, so it is 1 times 1, so we need 1 factor for each one of the double contributions, and also for the triple it is p minus 1, q minus 1, r minus 1, so it will be 1 also, 1 times 1 times 1. Okay, so now, and these add up to 7, so we have 7 degrees of freedom spent in estimating all these parameters, and the 8 remaining degrees of freedom, they go for the residuals. So now we compute what are the mean squares. So all these are dividing by 1, so we don't write them, but this one is dividing by 8, and then this is the mean squares of this residual, so it is 34. When I want to show whether something makes a difference or not, I have to compare its mean squares to the mean squares of the residual. So if I want to show that the species makes a difference, I have to compare the mean squares of the species, that is 500, to 34. So this is, I don't know, 12, 13 times more than this one. So that means that the species is really important, and it is significant. I would have to compute the f and compute the critical value for that f and reject it or not, but we see that something that is 15 times more explanatory than the level of noise, this has to be significant, and that happens for all these factors. What about this one? The species and moisture interaction, it is only 39. That is a little bit above only the level of the mean squares of the noise. Just for you as a kind of rule of thumb, something is so these f critical values, they are all somewhere between 3 and 4, more or less. Depends on the number of degrees of freedom, but it is a good rule of thumb. So if something is 3 or 4 times above the level of noise, then it is significant. So we see that 39 is not 3 or 4 times. This second order interaction between moisture and hormone is not either, and the triple interaction is not either. So very often what people do is to combine all these 3 lines that are not significant into something that is called lack of fit. So the lack of fit, the sum of squares is the sum of the corresponding sum of squares. It is using 3 degrees of freedom, and the mean squares is this one that is not significant. Okay, but all the others are significant. So now we have a lot of power, because we can see that when what we observe in an animal, part of it is coming from the species, and we know it is not in the table, but we know what are the main effect of that species. We know that it depends on the moisture. Actually, those are the 2 most important variables, because its mean squares that have not been calculated, it is not shown here because it is just dividing by 1. So its mean squares are so high with respect to this one. So these are the 2 most important variables. The hormone makes a difference, but it is not as important as this one. And then there is an interaction between species and hormone, meaning that not all species respond equally to the hormone. That is also a very interesting effect. And all this analysis capacity, you don't have it with the student t-test. So with the student t-test, you see that the mean of some of the groups is different from the mean of the other group. And also, for instance, here we have used so few animals per combination that when you make any pairwise comparison, it will not be significant. But here, with only 2 animals per combination, you are able to identify a lot of interesting effects. You are able to decompose the contribution of each one of the effects, so you know how much the species, the moisture, the hormone is doing, if there are interactions between factors. So you have a really an extreme power, analysis power. Okay, so here is a little bit of formalization. You can also introduce blocks, so you can combine blocks and factors and interactions in the same equation. So if you think that a male-female makes a difference, then for instance in the 2 animals that you have in each one of the groups, you can include 1 male, 1 female. So you don't have to make the experiment twice. You to estimate what is the contribution of the male and females. And we have the usual constraints. Here we have how to estimate the different components, and you see that sometimes the interactions they get a little bit more complicated, but the general idea is what is the mean of that interaction. So for instance, if we are analyzing the interaction between species and hormone, so what is the mean of frogs that have received the hormone minus whatever we have explained, and whatever we have explained is this part. So we have explained the overall mean plus the block and the contribution of the main effects. What we are trying to get is this one. So we can put it in a bit more complicated way, but anyway, it is easy. So what is the advantage? What are the advantages of factorial designs? So factorial designs can be allow the interaction of the allow the estimation of the interaction between factors, and we can assess its significance. So we have said not all species respond equally to the hormone. We have a wider validity of the main effects because they have been tested in many different cases. So the effect of moisture has been tested on frogs, toads, with and without hormone. So we have 4 different conditions, experimental conditions, to see what is the effect of moisture, and the same happens for all the others. And several experiments are done simultaneously, so the variance of pairwise comparisons is minimum, and we will see this in the following example. Okay, so let's say that you're allowed to have 24 animals to perform an experiment, this experiment with frogs and toads and hormone and so on. And let us say that we are only interested in the main effects. So if this is the case, then we could have 3 different designs. So the general wisdom in labs is, okay, you should keep everything the same and only change one variable. Okay, so we follow that wisdom. So we have, let's say, we have a reference group that is frogs dry with no hormone, and then we change one of the variables at a time. So we change frogs to toads, and then the other 2 we keep them the same. We will have 4 animals in each one of the groups, and now we can estimate what is the contribution of frogs and toads, but only in this condition, dry with no hormone. and then we take the same reference group, and now we change the second variable, so we change from dry to wet, and then we have 4 animals in each one of the groups, and the same for the hormone and non-hormone. And in total, if you count how many, so we have 6 groups, and each group has 4 animals, so we have a total of 24 observations. Okay, this is one design. The other possible design is, okay, if you look at this design, we have 12 animals that are frogs dry with no hormone. So that means that this group is overrepresented. So we can make all the groups to be equally represented. So we make all groups to have 6 animals, and then I will compare each one of these groups to this one, but this one is has also 6. So I would have, this is my reference group, frogs dry with no hormone, and I have 6 animals for that, and then in all comparisons I have 6 animals in each one of the groups. The factorial design makes, if you count here, you also have 24 animals. So the factorial design considers all possible combinations with each with 3 animals in each one of the combinations. So if you count, we have 8 possible groups times 3, so we have also 24 animals. So we have 3 possible designs, and each of them has 24 animals. So is any one better than the other? And the reason is yes. So at some point you will be interested in comparing the hormone, whether the hormone makes a difference or not. So you will have the hormone in 2 states, no hormone or receiving the hormone, and this one you will compute the difference between the two. So let's call it delta hormone, and this delta hormone is a random variable in itself. So if you repeat the experiment, you will not see exactly the same difference between the groups. So it has also some variability, and this variability is related to the variability of the residuals. And because we are subtracting two random variables, so the variance of this subtraction is the variance of the first one plus, not minus, the variance of the second. Okay, so what is the variance of each one of these groups? So let's see. So when we compare hormone, here we have 4 animals in each one of the groups. So the variability is we are computing the mean of 4 animals. So the mean of 4 animals, the residuals variance is divided by 4. So in the first experiment, we are dividing by 4 for that comparison. But in the second experiment, we are dividing by 6 in that comparison. So this comparison has 6 animals here, 6 animals here. So we are dividing by 6. But in the last one, if you count how many animals have received hormone and how many have not, you will have 12. So you are dividing by 12. So this comparison, the smallest variance is achieved in the factorial design. So the factorial design is the most accurate when reporting whether there is a difference between the hormone and non-hormone. And not only that, but here you know that in these 2 designs, you know that there is a difference in the hormone or not hormone, but only for dry frogs. What happens with other kind of animals and other experimental conditions, you don't know, you have not tested. But here in the factorial design, you have tested. So you have made all possible combinations, and you had 12 animals, and these 12 in each one, hormone, not hormone, and each one of these 12 animals, they were in very different conditions. So you had frogs, you had toads, you had dry animals, you had wet animals. So not only the comparison is much more accurate, but also it is much more generalizable in the sense that you have observed that effect in many different experimental conditions. So the general wisdom in the lab was keep everything the same and change one variable at a time. The general wisdom of factorial design is keep everything the same, so hold all factor constant except except those whose effects you are investigating, and then those you have to shuffle and combine as much as you can. So if you are interested in the species, moisture and hormone, you should keep all the other experimental conditions the same, but these three you have to combine them as much as you can. So with this we finish our first introduction to factorial designs, and then we will continue with more advanced concepts.